All right, class, we're going to move on into chapter 3. There was just that one section in chapter 1 we needed to look at. So hopefully you all have finished your I believe it was 1.2 assignment. Right here, as you can see, we're going to start looking at some number theory. And today we're going to look at prime and composite numbers. So hopefully you remember some of that. If not, we'll get it all cleared up for you. Past that. All right, so here's actually the things that we want you to be able to do. By the end of this lesson, I want you to be able to determine divisibility. You need to be able to write the prime factorization of a composite number. We are going to find the greatest common divisor of two numbers. We're also going to find the least common multiples of two numbers. All right, and then we'll look at a couple of problems that uses those things. But the main thing is being able to find the greatest common divisor and the least common multiple. And all that is based on using prime factors. So here we go. All right. Number theory is primarily concerned with the properties of numbers used for counting, namely 1, 2, 3, 4, 5, and so on and so on. So one of the sets of numbers, you've had these before, different sets of numbers, is called the natural numbers. It's also called the counting numbers. I need to make my pen. The counting numbers. And why would they be called the counting numbers? Because this is how you count, right? When you start counting, you start with 1 and you go up to count out as many as they are. All right. Natural numbers that are multiplied together are called factors of the resulting product. All right. So 24 is one of these numbers that has several sets of factors. 2 and 12 are factors of 24 because they multiply together to give me 24. So 2 is a factor, 12 is a factor. 3 is a factor of 24, 8 is a factor of 24 because 3 times 8 is 24. 6 and 4 are factors of 24. All right. Other factors of 24 are 1 and 24. Okay. So one sort of a weird one, it's the factor of all numbers. So it actually, we don't use 1 whenever we start talking about prime numbers or prime factorization here in a minute because 1 is a factor of everything. But anyway, these are factors of 24. Okay. All right, divisibility. Let's not make this any harder than it is. If A and B are natural numbers, A is divisible by B. If the operating dividend by B leaves a remainder of 0, that's the official definition, okay? Basically, all it's saying is B will divide into A evenly. 12 slash, we'll call that slash 24. We can write that because 12 divides into 24 evenly and leaves a remainder of 0. If we write 13 slash 24, that means 13 divides 24, but it's not true. So this is not true. Okay. So when you get to your assignment, or you get to a quiz or a test, it's just going to give you something like this: 2, 3, 15. It's going to ask you, is that true or not? Will 2 divide into 315 evenly? And the answer is no. It would have a remainder. All right. If I had 330, is this true? Yes, this is true because 3 will divide into 30 evenly. So this would be a yes. So that's all that's asking. So don't make this any harder than it is. It's sort of, you don't see it a whole lot, but that's all they're asking for. It's just a little thing looking at the divisors and being able to be divisible. And there's a blank screen. Oh, maybe it'll pop up. Let's see what's going on here. My screen is blank. I don't know why that's there. That should be okay. So let's talk about prime factorization. That was weird. I don't know why those were blank, but they are blank. Here we go. A prime number is a natural number greater than 1 that has only itself and 1 as factors. All right, so 1 cannot be a prime number. It has to be larger than 1. All right, and it's a number that can't be divided by anything other than itself. All right, the first few prime numbers are 2, 3, 5, 7, 11, 13, so on and so on. None of these numbers have any numbers that will divide into them other than themselves and 1. One thing about the number 2 is the only even prime number because every other even number can be divided by 2. All right. So there's our prime numbers. You could keep taking that list out. The composite number is the opposite. It's any of the other numbers greater than 1 that is divisible by a number other than itself and 1. The number 4 can be divided by 2, can be divided by 4, 6, 8, 9's the first odd composite number. 9 has a factor of 3 and 9, and that goes on forever, but that's composite. All right, the fundamental theorem of arithmetic states that every composite number, every one of these numbers right here, can be written as a product of its prime numbers. Remember, product means multiplication. So you can take any one of these numbers and you can multiply prime numbers together to get that number, right? 4 would be 2 times 2. 6 would be 2 times 3. 8 would be 2 times 2 times 2. All right. And one of the ways we go about finding prime factorization is using the factor tree. So that's what we'll be doing a lot of today, is using the factor tree. All right. So if we want to find the prime factorization of 700, we start with 700, and then, we start making branches. The 2 branches underneath 700 are going to be any 2 numbers that multiply together to give me 700. They chose 7 and 100. I didn't have to use that. I could have used 10 times 70. All right. Notice once they got to a prime number at the end of a branch, they circled it there. 100 is not prime. It can be broken down to, say, 2 times 50. 2 is prime. 50 is not. 50 will break down to 2 times 25. And then 25 will break down to 5 times 5. All right, now watch if I'd have done it this way. 10, it's not prime. It breaks down to 2 times 5, which are both prime. So those are prime numbers at the end of my branch. 770 is 7 times 10. 7's prime. 10 can break down again, 2 times 5. Now notice, it doesn't matter how I did either one of these. The prime factorization for 700, notice there are 2 2's here. There's 2 2's here. There's 2 5's over here. There's 2 5's over here and a 7. So the prime factorization of 700, written out the long way, is 2 times 2 times 5 times 5 times 7. Now, most of the time we want to go ahead and shorten that up, and we're going to use exponents. 2 times 2 is the same thing as 2 squared. 5 times 5 is 5 squared, and then 7 is by itself there. So those are the prime factorizations of 700. That's the prime factorization. That is the prime numbers multiplied together that will equal 700. Every number that is composite can be broken down in this manner. All right? And there's what we just wrote. So I'm going to go on. So let's look at the number 462. All right. So if you're at home, distance learning, why don't you push pause real quick and see if you can prime factor 462 as I go ahead and do it. So we've got to come up with 2 numbers that multiply to 462. Well, here's where there's a few things you can use to help you. Is number 1, if it's even, we always know 2 will go into an even number. All right. So this is even. So I know it's going to be 2 times something. 2 will go into it 231 times. All right. What about 231? Well, there's a couple other tricks. All right. You could just get your calculator and starting with 2, go 231 divided by 2, 231 divided by 3, 231 divided by 4, 231 divided by 5, and till you get a number that goes into it evenly. All right. Couple tricks. I know that numbers that are divisible by 2 are even. This is odd, so it's not going to be 2. A trick for the number 3 is if you add up the numbers in the digits in the number, 2 plus 3 plus 1, 2 plus 3 plus 1 is 6. If that number is divisible by 3, then the entire number is divisible by 3. So since 6 is divisible by 3, 231 can be divided by 3. So if I go 231 divided by 3, that's going to be 77. Then we know numbers that double up like that are divisible by 11. So that's going to be 11 and 7. And there are my 4 prime numbers. Notice I don't use 77 and 231 in my prime factorization because they're not prime. I got to get down to the prime numbers. So the prime factorization of 262 is 2 times 3 times 7 times 11. You don't have to put them in numerical order, but my mind works to where I like to see them in numerical order. All right, so that's the prime factorization of 462. All right, now get into the meat of our lesson here. Finding the greatest common divisor. It's also known as the greatest common factor. All right. And one area you do this is if you are adding fractions, they got to have a common denominator, right? Well, what you do is you find the greatest common factor. No, I'm sorry. That would be least common multiple. Or greatest common factor. I don't know. I can't think of it right now. But this is something that you can use when adding fractions, I do believe. I was right the first time. All right. So here are the steps. You're going to write the prime factorization of each number. All right. Select each prime factor with the smallest exponent that is common to each of the prime factorizations. Form the product of the numbers from step 2. The greatest common divisor is the product of these factors. All right, so what exactly is the greatest common divisor or the greatest common factor? Well, if I have two numbers, like the number 6 and the number 18, no, let's use 9. All right, what are all the factors of 6? What are all the numbers that will multiply? We've got 1 times 6, 2 times 3. 9 is 1 times 9, 3 times 3. So what is the largest number that appears as a factor of both? Well, the 3 is the greatest common divisor, the greatest common factor. Okay? So that's what the greatest common factor is. All right? Numbers that have 1 as the greatest common divisor are called relatively prime. Okay? For example, the greatest common divisor of 5 and 26 is 1. Thus, 5 and 26 are relatively prime. Okay? So, yeah, as I thought about it here, this is not like least or finding the common denominator. That's least common multiple. All right, got a little bit confused with that, so I want to make sure you're clear on that. That's going to be in a moment. So let's talk about finding the greatest common divisor. All right, now between 6 and 9, it was real easy. I could just list them. But when the numbers are bigger, like 216 and 234, I don't want to go through and list all the different factors of each one. So here's what we're going to do. And I'll explain what all this set up here. I didn't really spend a lot of time with this stuff up here because I'm going to explain it to you down here. It makes more sense as we're actually working through it. So what we're going to do is we're going to prime factor each one. So 216 is 2 times 108, which is 2 times 54, which is 2 times 27, which is 3 times 9, which is 3 times 3. So here are my prime factorization of 216. It is 2 to the third times 3 to the third. 234 is 2, and that's 117. All right, 7, 8, 9. When I add those up, 9 is divisible by 3, so 3 will go into that. So that will go 39 times, I do believe. All right, 39 is another one divisible by 3. That'll go 13 times. And there we go. We have 2 times 3 squared times 13. Okay, so I've got the prime factorization of each one. All right. Now, here's how I find the greatest common factor. All right, between these. And here's how it goes. I'll look at the base factors of each one. If I have a factor that shows up in one factorization but does not show up in the other, I cross it out. It is not a common factor between these two, right? This one doesn't have a factor of 13 in it, so it's not common. Well, what's common between here? Well, there's a 2 that's common, and there are a 3 that's common. Now, this is 2 to the first power if it doesn't have an exponent. All right. What we use if we have the factor common to both is we use the smaller exponent. So I would use 2 to the first. And here, what's smaller between 3 and 2 is 2. Now, if they happen to be both the same, you just use one or the other. You don't use both. You just use one of them. Okay, because if I had 3 to the third and 3 to the third, then the 3 to the third is common to both, so I would use 3. Okay, like there's 2 of these common, there's 1 of these common. That's why I use those. All right. Now, what I do is I just multiply that out. 2 times 3 squared, that's 2 times 9, which is 18. So 18 is my greatest common divisor or greatest common factor between those two. All right. So we prime factor each. We list the factorization. Any factor that only appears in one of the factorizations we cross out because it's not common. All right. Then we list the ones that are common, and then we use the lower exponent. Okay. That's how we find greatest common factor, greatest common divisor, however you like to say it. All right, let's try these two. What's the greatest common factor or greatest common divisor between 400 and 285? If you're at home, you want to stop, put pause, and see if you can do this on yourself. That would be good. So let's go ahead and let's see. This is going to be 40 times 10. 4 times 10. 4 is 2 times 2. Those are both prime. 2 times 5. Those are both prime. And 2 times 5, both prime. So what I have, 4 2's, 2 to the 4th times 5 squared. 285. All right. Any number that ends in 5 or 0, I know is divisible by 5. So I'm going to say 5, and that will be 57, I think. Now, I don't know about that. 7 plus 5 is 12, so I know 3 will go into it. So that will go 19 times, and 19 is prime. So there we go. We have 3 times 5 times 19. Now, greatest common divisor. If a factor shows up in one and not the other, it's not part of our grouping here. So here, there's 2 here. There is not a 2 in this one, so I'm not going to use 2. There is 5s in both of them, so I'm going to use 5. All right, there's not a 3 in both. There's a 3 down here, but not up here. I'm not going to use 3, and 19's down here, but not up here. I'm not going to use 19. Now, which is the smaller value of 5? That's what I use, is 1. And all I have is 5 to the first power, so the greatest common factor of these two numbers is 5. All right, would have thought it was a bigger number between those two, but it is 5. All right, that is greatest common factor. All right, I think we're going to look at a problem here. Nope, we're going to go right into least common multiple. All right, so least common multiple. All right, now here's the difference between least common multiple and factor. Multiples are numbers that you multiply to get the next one. So, right, multiples of 5 are 5 times 2 is 10, times 3 is 15, 20, 25, and so on. These are multiples of 5. All right. So if we are comparing two numbers, such as the number 6, let's go to 6 and 9 again, like we did for factor. Okay. What are multiples of 6? Well, 6 times 2 is 12, times 3 is 18, times 4 is 24, 30, and so on. 9 times 2 is 18, 9 times 3 is 27, 36, so on. And then what we're looking for is we are looking for the first one of these multiples that matches up. And here they are, 18. That is the least common multiple. All right, now this is when we are, let's say we had a fraction 1/6 plus 1/9, and we had to add these two where you have common denominators. I would use the common denominator of 18 or the least common multiple. Okay, so that's where this comes into play. All right, here is the steps. Write prime factorization, write it out just like we did before, and form the product of the numbers from step 2. The least common multiple is the product of these factors. All right, so it says select every prime factor that occurs, raised to the greatest power, so that's important to remember right there. And the other is we have to select every factor that shows up. So here's what that means. Let's look at this. All right, so we've got 144 and 300. First part is we're going to do the exact same thing we just did, is we're going to find the prime factorization. So 144 is 12 times 12, 2 times 6, 2 is prime, 2 times 3, prime and prime, 2 and 6, 2 times 3, prime, prime. 300 is 3 times 100. 100 is 10 times 10, 3 is prime. 2 times 5, both prime. 2 times 5, both prime. So the prime factorization of 144, there is 3 2's, 2 to the third, and 3 squared. Here there is 2 2's, a 3, and a 5 squared. All right, now for least common multiple, it's sort of the opposite of what we just did. For greatest common factor, if a factor showed up in one and not the other, we crossed it out. Well, in least common multiple, if a factor shows up in one and not the other, we use it. So I've got to use 5 squared because it's not in the other one. I use all factors that show up. So 5 is a factor. I have to use it. All right. Now, the other ones, for the factors that show up in both. Well, for greatest common factor, I would use the smaller amount. For least common multiple, I do the opposite and I use the larger amount. So 2 shows up in both. I'm going to use the larger amount, 2 to the third. 3 shows up in both. I'm going to use the larger amount of 3 squared. So then I multiply these together. So that's what? 25 times 8 times 9. And let me pull my phone up over here and see if I can't do that on my calculator. 25 times 8 times 9 is 1800. So the least common multiple is 1800. So what you're going to run into is least common multiples. It says least, but it's going to be larger than the two numbers you start with. Factors are going to be smaller than the two numbers you start with, right? Because we're looking at factors. Multiples are numbers as they keep going up and up. So that lets you remind you that the multiples are bigger, factors are smaller than the numbers you start with. Okay? So let's look at all right, so we're going to go on to a application problem here. Okay? A movie theater runs its films continuously. One movie runs for 80 minutes, the second one runs for 120 minutes. If both movies begin at 4 p.m., when will the movies begin again at the same time? So basically, this is a least common multiple problem. All right, this one starts for 80 minutes, then it starts again. This one goes every 120 minutes. So they want to know at what time will they begin again at the same time. All right. We are asked to find when the movies will begin again at the same time. Therefore, we are looking for the LCM, lowest common multiple of 80 and 120. So let's do that. Let's find, I don't like it doing it like that. Let's go right over here. I'm going to go off to the side, and I'm going to find 120, and I'm going to find 80, and I'm going to find out how many minutes, what multiple of minutes do they match up again, or what is their least common multiple. So 120 is 12 times 10, 3 times 4, 2 times 2. Prime number, prime number, prime number, 2 times 5, prime number, prime number. So there's 3 2s, a 3, and a 5. 80 is 8 times 10, 2 times 4, 2 times 2. My 2's are prime, 2 times 5. So there's 4 2s times a 5 there. So my least common multiple, any factor that shows up in one but not the other, we use. So we have to use 3. All right. Factors that show up in both, I use the larger. If they're equal, then I just use one or the other. So for the 2's, I'm using 2 to the 4th. For the 5's, they're the same, so I'm going to use 5. All right, so I've got to multiply 3 times 2 to the 4th times 5, which is 3 times 16 times 5. And every 240 minutes, the movies will restart at the same time again. Now, does that answer my question? No, it doesn't, because it asks me what time will that be? Well, 240 minutes after 4 o'clock is going to be what? Well, what's 240 divided by 6? And we can figure out how many hours that is. Divide that by 6. That is not 40 hours. 240 minutes divided by 60, not 6. There's 60 minutes in an hour, not 6. So 240 divided by 60 is 4. So 4 hours later, these two movies will sync back up and start at the same time, which will put us 4 hours past 4 p.m., which would be at 8 o'clock p.m. All right. So that is our least common multiple, a problem we use with it. And I think that is it. So I will open up assignment 3.1, and that's what you need to be working on. We probably will have this work on this through Wednesday, and then Friday we'll start another. So